welcome back to Statics 1. Previous lecture, I showed you an example of the parallelogram law and how we can use that to find the magnitude and direction of a resultant vector. In this case, I'm going to show you another example where we know the direction of the resultant vector, but we don't know its magnitude. So here we have, in fact, we don't even know the magnitude of the other vector that is a component of the vectors. And let me introduce that term component. You'll see that frequently in textbook. So if you have a resultant vector, which is adding together two vectors, the components of that vector are those two vectors. So you have components and resultant vectors. All right, so in this case, we have a component vector f1, component vector f2, and a resultant vector. So if you add those two vectors up, you come up those two component vectors, f1 and f2, you end up with our resultant vector, fr. And we know the angles of our component vectors. We know the magnitude of one vector, and we know that a resultant vector, we're told, is in the vertical direction. My first intuition on looking at this problem is, wow, I don't think we have enough information. So it's kind of interesting to see, in fact, that you could solve this problem. And what I'm going to do is I'm going to do it first graphically using the parallelogram law, and then we'll do it quantitatively using the sine law. Okay? So how do we do this? We know the I drew the resultant vector and our vector f1 in blue because we don't actually know their magnitudes. In other words, we don't know how far up on the page they're going to go. So let's start here at this point, the head of f sub 2, which is 30 degrees from horizontal, and we know to be 200 pounds. And so when we do the parallelogram law, I'm going to draw it. And again, this vector, f1, is 45 degrees from horizontal basically off in this direction. So we're going to draw, I'm going to try to do it as well as I can, like this. Let's see how it looks. Oh, pretty good, not too bad. So this is parallel to that, and it almost went through the head of this thing. If I had a straight edge, might do a little better. So this is 45 degrees. We know we're going to have, right here, that's going to be 45 degrees as well, okay? Now, we know that f of r is going to intersect this. If we're going to draw our parallelogram, we know that f of r is going to intersect this directly. Because we're told f of r is vertical, we know it's going to basically intersect at that point. So we can, in fact, draw our resultant vector. I'll do it in green. Here is our resultant vector. Perfect. Not a problem. So we've done this graphically. There's f of r. And now we can use the parallelogram law again to find out how far out this f1 vector is going to go. All right, so let's do that. So we're going to start here at the head, and then we're going to draw a line here that's parallel to this line. We'll try, and let's do it. Well, I did the other one in blue. Let's do this one in blue as well. So 30 degrees. Not bad, not bad. So that's 30 degrees. And now we could draw our other component vector, f1, which we know is going to intersect here. So we've done this graphically now. This is great. So now, in fact, my intuition of whether we could actually had enough information to do this, we've proven that to be wrong, because now the parallelogram law showed that we were able to figure out what f1 is, what f of r is. But we don't actually, as yet, know the magnitude of fr or f1. And we're going to find that. So what else do we know here? This is 30 degrees. This is going to be 60 degrees, right? Because 30 plus 60 is 90. And this one, because we have two parallel lines, and we've drawn this line through that, we know this to be 30 degrees. So that's 75. So we could actually come up with this. I don't think we actually need that value, so I'm not going to bother doing that. And now we can use the sine law, right? So the sine law just relates the ratio of the length to the opposite angle, right? So in this case, we have our length, f of r. So I'll just write it out here. A over sine A equals B over sine B equals C over sine C. You remember, A, B, and C, those are the lengths of our, the legs of our triangles. A, lowercase a, lowercase b, lowercase c, those are the angles of the opposite, opposing. This would be the angle opposing A, angle opposing B, and angle opposing C. All right, so in this case, we have f of r, and the opposing angle is over here, 75 degrees. So sine of 75 degrees equals. So what else do we know? Well, we know this angle, so let's use this opposing force. Oh, we don't know that one, so we're going to have to use, this one is 200. So we have here 200, what are they, pounds? And so what is this angle? I'm going to put sine, and I'll leave this blank because we don't know yet. But we know that you can add the three angles of a triangle and we get 180. So we have 60. I better do this in a better way. And I wish I'd done this first, but let's do it here. We're going to say that 60 degrees plus 75 degrees plus this angle, which we're going to call alpha, equals 180 degrees. So we can say that alpha equals 180 degrees minus 60 degrees minus 75 degrees equals 45 degrees. All right, so this is 45 degrees. So now we can do this. So this, if I was to do this on paper, I would want this to be above this because we're going to put this in here. So I'm going to kind of box this off and say this should have gone here as a step prior to this step. So it's a little not quite as neat as I hoped it to be. And how do we find out? So we can just find out f of r equals 200 pounds times sine of 75 degrees over sine of 45 degrees. And we're going to get f of r equals, and I'll just look up the answer, f of r equals 273 pounds. Okay, so that's my answer. I'll put a box around this, so we know that's our answer. So this is now a known value of 273 pounds. All right, so now we need is what is our f of 1 value? And can we do the same trick using the sine rule? In fact, we can. So this f of 1 here, this distance is the same as that distance, right? It's a parallelogram. So we can apply our same technique of using the sine rule. And am I going to have enough room to do it here? I'll try. So we have f of 1 over sine of what angle? So f of 1, the opposite angle is sine of 60. The opposite angle is 60. We have sine of 60 equals, and now we can pick and choose which one we want. I'll use this one is 200. I'll use that because it's an exact quantity, whereas this is known only to 3 significant digits. We're going to have 200 pounds over 200, and the opposing angle is 45. So we have sine of 45. And then we can do the algebra here, and I'll just write the answer, and you can find that to be sure that you know it. You should get f of 1 equals 245 pounds. Okay, so that's our other answer, which is the magnitude of the resultant vector. So let's just look again what we did. We started off where we knew the directions of the component vectors and our resultant vector, and we knew the magnitude of one of our components. In this case, it was 200 pounds. And we applied, then we figured out what the angles were within our triangle, and then we successively applied the sine rule, this one here, to obtain first f of r, the magnitude here, and then the sine rule to find f of 1 in this case. And let's look at the results to see if they make sense. So we have 200 pounds this way, 245 pounds over here, 45 pounds, and then 273 in that direction. You know that they're kind of counteracting each other, so that kind of makes sense that they'll end up being vertically. They're more or less the same magnitude, and then we would expect, in fact, the magnitude in this direction to be greater than the magnitude of each of these, so that makes kind of sense. So I like the answer, and in fact, it's the same answer as they have in the book, so I'm quite happy with that. So this is it. Make sure you know how to do this problem. You will definitely see one of these on a test and in your homework problems. So I will see you in class. Bye.